Welcome back. This is Larry Benko W0QE. In this video is a short video about one and only one topic, that is impedance. Now in SimSmith, impedances can be referred to as capital Z, capital ZN, invZ capital Z, revZ capital Z. They all mean different things. And within the Ruse block, you also have capital Z and small z. I'm going to go over all of those and hopefully clear up any doubt people have with regard to what they actually are. Let's begin with a simple SimSmith circuit that has a 15 ohm resistance for the load, has a 10 ohm resistance in series here, and it has a series LC circuit. And let's look at the impedance that exists within this circuit as we look different directions. Now we're going to sweep this circuit from 2.5 to 20 megahertz. This LC circuit is resonant at 10 megahertz right there. And the components have a Q of 0. When you put 0 in SimSmith, that means they have a Q of 1 million. And we're going to drive it with a 1 watt 50 ohm generator. And it's got a power output of 1 watt. You don't need to have parentheses 1 here. You can just forget that. You get 1 watt by default. You could put parentheses 4 here. You'd have a 4 watt generator. It's a 50 ohm generator. Wants to see a 50 ohm load. Anything less than that, you'll have mismatch loss. And let's look at this circuit. Now, I made a note block here that describes what's going on. I also made a block here that shows it a little more graphically. The notes block is really nice to be able to put stuff in a SimSmith circuit to remind you if you go back and look at it a month later what's actually going on. This is just done for the video though. So let's look at what we have. We have a component here. We actually have 4 components in this circuit. Let's take one of the inner components. The inner components have 2 sides to them. The load only has a right side. The generator only has a left side. And by the way, this whole analysis works just fine if we turn the circuit around backwards. Everything I say right now just basically means left becomes right, right becomes left, etc. So the first thing let's look at is component.z. Now component here is named L, LC1, R1, or G. So that's the component name. And then we follow it with a dot z, dot revZ, invZ as to what we want to look at. So component.z is the impedance looking towards the load from the generator side of the component. So in this load right here, L.Z would be the impedance looking left from this side of the component. Likewise, Zn is the same thing except we're looking from the left side of the component. We're still looking we're looking towards the left. And we can also look from the right side of the component back towards the generator. And then finally we have this interesting one, which is invZ. It says what impedance to the left side of the component, if we say L.invZ, we can say what impedance to the left side, to the left of this component would be such that the generator would see an impedance of G.Z0. And that basically means the generator is matched. So that's very interesting, and this is extremely powerful if you want to see what the matching range is for a circuit or something like that. Let's just begin. Let me close this one. Oh, and by the way, if you don't have a left side of a circuit like L doesn't, then L.Zn isn't allowed. And if you don't have a right side to your circuit like the generator, G.Z, G.invZ, and G.revZ are also not allowed. Let's take this and just move it up here. And let's look at L.Z. And as we'd expect to see, it's 15 ohms. It's the impedance here looking left. Let's look at LC1.Z. LC1.Z. It is now a swept value. And the reason it's swept is we're sweeping the frequency from 2.5 to 20 megahertz. This LC circuit at 10 megahertz, which is where the green circle is, 0 ohms here, which means we still see 15 ohms if we were here looking left. At the high frequency end, which is 20 megahertz, this circuit has a reactance of plus J10, and that shows right there. And at 2.5 megahertz, this circuit has a reactance of minus J I didn't quite get on it, but it's minus J25. Let's look at a few more things. L.Z was looking this way. LC1.Zn should be exactly the same as L.Z. And we see it is. Going over here, LC1.Z looking this way is the swept value. And we also have R1.Zn, which is on the left side looking this way. R1.Zn, again, will be the same value. Likewise, one more time, let's do it again. R1.Z is the impedance looking this way. That is now 10 ohms more than what we saw when we were here looking left. So now it's 25 ohms at 10 megahertz. It's 25 plus J10 at 20 megahertz. And it's 25 minus J25 at 2.5 megahertz. And likewise, G.Zn will be exactly the same impedance as R1.Z. Now, let's get rid of all those. For the moment, and let's look at the other two types of impedance. revZ. For L.revZ, let's see what that looks like. Now, that shows the value. So at 10 megahertz, what we see here is, I didn't quite get on there again, it's 60 ohms. This point right here, looking this direction, so we're looking from the right side of the component towards the generator, we see 50 plus 10 plus nothing at 10 megahertz. Up here at 20 megahertz, we see 50 plus 10 or 60 plus J10, which is shown right there. And at 2.5 megahertz, we see 50 plus 10 minus J25, which is 60 minus J25. And likewise, we could look at LC1.revZ. I'm going to find it here. And we see it's just a dot. It's a dot at 60 ohms only, and that's exactly what you'd expect, 50 plus 10 ohms. Let's look at the final one, invZ. Let's start with L.invZ. Let's move this out of the way again. L.invZ, looking right here. What impedance over here would match this to G.Z0, which is 50 ohms? So what we see is at 10 megahertz, we see, again, this should be 40 ohms. 40 ohms. So if we put a 40 ohm resistor in here at 10 megahertz, we would have 40 plus J0 plus 10. 40 plus 10 is 50. 50 plus J0, and that would match. At 20 megahertz, we would need an impedance here that would look like 40 minus J10. So 40 minus J10 here at 20 megahertz, this would be plus J10. So then that would be 40 total. So if we were to look right here, looking to the left, when this was 40 minus J10, we'd see just 40 ohms plus the 10 ohms, and there's our 50 again. Likewise, at 2.5 megahertz up here, if this was 40 plus J25, and at 2.5 megahertz, this was minus J25, that would again be just 40. 40 plus 10 is 50 again. So if this was our matching network, we were trying to figure out what range it would match to, this would be the function we would use. And of course, we don't have to go to L.invZ. We could do LC1.invZ, etc., etc. Of these, component.Z is what SimSmith provides you here automatically. With the exception of G, there it's component.G, it's G.Zn. So R1 and G will always give you the same value. You probably noticed this if you use SimSmith very much. You see that they're exactly the same. If you want any of the other ones, you have to come up with them yourself. Now, they're not very hard to do. Let's get this thing out of the way again. What I did is I said plot on the Smith chart L.Z, and it gave me that for the name if I didn't specify a new name that I wanted to use, L.invZ, L.revZ, and likewise for all of them. I got a couple other things I'd like to show you real quickly here too. If we plot on the Smith chart, we have nothing plotted right now. Let me get rid of this. And let's plot A. Well, here I declared we're going to plot with dots. We're going to, when the function name is going to be A, so we see A here. And if you look closely at what we have here, we have 10 points that are logarithmically spaced from 2.5 to 20 megahertz. So there should be 10 dots here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they represent the line that would have appeared if we had plotted a line. These are the individual points that were actually asked for. And SimSmith did the filling in of the blanks. And we said plot dots. Let's look at the second one. It's the same thing, except I said plot diamonds. SimSmith can plot all kinds of shapes. Dots, diamonds, triangles, stars. And it's the same plot again. Likewise, if we go over here to C, we see triangles. Now, let's go to the last two real quickly. This one, stroke 6. That's a fat line. It's no longer discrete like the dots were. It gives me a continuous line, but it's extra wide. If I want to do something, I want it to be bold and I want it to show up, I can do this. If I want it to show up and I want it to be dotted, this is a slightly less wide width lines, four dots wide. I have 8 dots of line, 6 dots of gap between them, and I can, you can mess around and do these as much as you want. I've discussed this in previous videos, but this is just a reminder that this all applies still with no matter what you're plotting. Let's look at the Ruse block real quickly. And now we have a SimSmith circuit which consists of a generator which has a 10-volt absolute voltage source. That's 10-volt source with no output impedance. And that's to make the analysis of the Ruse block a little bit easier to do without a calculator. A Ruse block and 50 ohm load. In the previous example, we showed that there were 4 different ways to measure impedance: .Z, .Zn, invZ, and revZ. And they still work the same way with the Ruse block as they do with any other SimSmith block. However, the Ruse block has 2 additional ways to measure impedance: .z and .Z. This Ruse block consists of 3 resistors, and I set the values in 3 different ways. The first way, and that's just done to remind everybody how you can do it. If you do nothing, SimSmith gives you this way of doing it. You get a reference designator, and the value for the component is R3 underscore. You're given a parameter, R3 underscore, that you fill the value in. So this is a 5 ohm resistor in this example. Here I've defined the value to be a variable, RS. In this case, RS is a parameter that SimSmith gives you once I enter it here. And again, it's another 5 ohm resistor. The third way is just to put the value in the circuit directly. And this is a 75 ohm resistor. If we look at R1.z, that's defined as the voltage across R1 from pin 1, which is where the dot is, from pin 1 to pin 2, divided by the current that flows into pin 1. And of course, these are complex numbers based on phases and everything else. In this circuit, since everything's a resistor, all the phases are 0, and it makes it easier to show what's going on. But they can be reactive components just fine. The second way of doing it is R1.Z. And this is a little bit different. This is defined as the voltage from R1 to circuit ground, and it's circuit ground in this circuit only, not a ground definition in some other block, but just in this block. So in this case, it's this point right here. So it'd be the voltage from here to here divided by the current flowing into pin 1. Now, if the circuit looked like this, so that there was no reference to ground within the circuit at all, P2.pin2 would be used as the ground reference if there's no connection. However, if I made a connection here, then this would be the ground reference, and we would look at the voltage from here to here divided by the current flowing into here for R1.Z. Here's a drawing that shows this a little bit better. In this case, we see this case right here is either this one or this one. They're identical. What we have is we have a source that's 10 volts. Since this is defined to be ground, this is 0 volts here. This is 10 volts. Then the current that flows. If you do some simple arithmetic and a little bit of algebra, 75 ohms in parallel with 50 ohms is 30 ohms. So this is a 30 ohm effective resistance, these two in parallel, with a 5 ohm in series and another 5 ohms in series. That's a 40 ohm impedance. 40 ohm impedance gives us a 1.25 to 1 SWR, which we see right here. See 40 right there is the input impedance. If we calculate the current with 10 volts, we see 0.25 amps flows. 0.25 amps flows through R1, 0.25 amps flows through R3, this direction because this is the phase. So the phase is here, so the current's really coming out. So we see this current that flows into pin 1 as a negative value because the current's really flowing out here. In this case, the dot is in the direction of the actual current. So we see this is being 0.1 amps, and this would be over here 0.15 amps. This would be 0.25 amps, which would be the same current as through these two resistors. Now, if we look at R1 dot small z, that is 10 volts minus 8.75 volts, which is 1.25 volts, divided by 0.25 amps. So R1 dot small z is right there, and that's 5 ohms, which is just the value of the resistor itself. R1 dot capital Z is 10 volts minus 0 volts here. So it's 10 volts divided by 0.25 amps, and that shows as 40 right there. R2 dot small z is 8.75 volts minus 1.25 volts, or 7.5 volts, divided by 0.1 amps, which gives us 75 ohms. And R2 dot capital Z is 8.75 volts, which is the point here, divided by 0.1 amps, or 87.5 ohms right there. Now, if I change the ground reference, some things change. We're looking at this circuit now. In this circuit, with the ground reference defined to be here, this is 8.75 volts, this is 7.5 volts, this is 0 volts, and this is minus 1.25 volts. Again, 10 volts across here, but with respect to the ground being here, this is 8.75 and minus 1.25. R1 dot small z now is 8.75 minus 7.5, or again 1.25 volts divided by 0.25 amps, which is 5 ohms. R1 dot capital Z is 8.75 volts divided by 0.25 amps, or 35 ohms. R2 dot small z is 7.5 minus 0, which is 7.5, divided by 0.1 amps is 75 ohms, and we see 75 ohms right there. R2 dot capital Z is 7.5 divided by 0.1, and it's again 75 ohms. I don't use the capital Z function very often, but it's available, and it was put into SimSmith, and I just thought I'd mention it. Anyways, this is all I really wanted to discuss in this video, but there's several different ways to look at impedance in SimSmith, and of course you can do it yourself via formula anytime you want. You can take any voltage at any place in the circuit and any current that flows into that point in the circuit and calculate an impedance directly. If you like the video, let me know. If it's too complicated, let me know. If it's too simple, let me know. But nevertheless, these are some features of SimSmith that in certain applications are quite useful. And the invZ feature I'm going to feature prominently here in a few upcoming videos where I'm going to talk about different antenna matching networks and what ranges they match and those types of things. Hopefully everyone's having a good time while we're sequestered at home, and there'll be more videos.